Yes, there will be a recording. It could take me a little while to get it up on the YouTube site, but as soon as I can, I will get it up on the UCLA OARC YouTube site. Um, Andy or Katrina, if you could pop that URL in the chat, I would appreciate it. Thank you. Thank you, Andy. All right, we're going to wait for probably one more minute to let folks show up, and then we will get started. All right, we're going to go ahead and get started now. And if other people join along the way, that's wonderful. Thank you for coming today. My name is Christine Wells, and I am with the UCLA Statistical Consulting Group, or Statistical Methods in Data Analytics. I think that's what they renamed us as recently, but we're still the UCLA Statistical Consulting Group. I am joined today by actually all of the consultants came today, so that's super cool. Andy Lynn is here, Siavash Jalal, Katrina. Oh, Katrina, I'm going to mispronounce your last name. I'm sorry.
It's okay. It's Kayohita.
Yes, okay. Katrina's here, and Shars is here as well. When I'm presenting, I'm not able to see the chat at all, so they will be monitoring the chat. However, we've got a fairly small group today, and so if you would like to just unmute yourself and ask questions as we go along, that is perfectly fine with me. I actually kind of prefer it because then at least I know somebody's still there. But we do have a full session today, so why don't I share my screen and let's get going. Now, I do have all the stuff up on our website. This is our website, stats.oarc.ucla.edu. If you hover over resources and come down to the seminars tab, you can click on that. Now, for this quarter, you can see the workshop notes are posted here, but in future quarters, what's being presented that quarter will be there. And so you will scroll down here and then click on this link. Currently, those go to the exact same page, but in the future, you're going to have to come down here and click on this. And this is a super exciting page, you can tell, right? The PowerPoint had to be broken up into part 1 and part 2, just because of size limitations uploading it. But you just go through part 1 and then click on part 2. Here's the link to the example data set that we're going to be using. Here's the link to the syntax that's used throughout the entire workshop. And then wait until we're all done and you've tried it. Here are the answers to the questions in the workshop, but try not to take a sneak peek before you give it a try for yourself there. So that's what we have. If you do not have SPSS installed on your computer, or you don't have the complex samples module licensed on your installation, don't worry about any of that now. Just listen. All the syntax and all the output are contained on the slides. That's why there's so many slides. Everybody who's used SPSS knows that SPSS produces a lot of tables in the output, and I put all the tables on slides. I tried to put lots of tables on one slide, you know, to kind of minimize it, but there are so many slides because there's just so much output here. So if you don't have SPSS installed or you don't have complex samples right now, don't worry about it. You will still be able to see exactly what's going on. You will be able to see the output and everything else. All right, so without further ado, let us dive into applied survey data analysis using, and I'm using version 29. I believe that if you're using version 28, 27, 26, maybe even back to 25, all of this will be exactly the same. I don't remember seeing any recent updates to what's available in the complex samples module. So if you're not using the current version of SPSS, definitely do not panic about that. You should be just fine. All right, so what are we going to cover today? Of course, we have to start off with some definitions and all that kind of good stuff. We're going to talk about what complex survey data analysis is and is not. What are these elements here that make complex survey data different from other types of data? We're going to use most of the commands in SPSS Complex Samples to help you do the analysis. And of course, we'll discuss the interpretation of the results. Spoiler alert, it's just like interpreting any other analysis. There's nothing special because we're in complex samples. So at least that part will be nice and easy. Now, there are some things that we are not going to cover. I'm not going to cover, the CS here is for complex samples. So when a command name starts with CS, it means complex samples. We're not going to cover CoxReg. That's a type of survival model. Just because if you're not familiar with survival, none of that's going to make any sense. And I didn't want to bore audience members. So we're going to skip that. CS select is used when you have a population and you want to create a sample from your population. We're not going to cover that kind of situation today, but that command is there if you ever find yourself needing that. We're not covering weighted multi-levels, weighted propensity scores, methods for handling missing data or graphing either raw data or results. That's not included in today's presentation. Alrighty, so let's start off with some common questions. What are complex survey data and how are those data different from other types of data? Without looking at the next slide for the answers, would anybody like to unmute and answer one or both of these questions? Please? Somebody unmute. Give it a shot. Be brave. Yes. Unmute yourself. Say hi. Answer the questions. Give it a go.
Hi, this is Ben here. Complex survey, I think any random survey that the individuals have not the same equal chance to be part of the survey. So if we design the survey so that not everyone has the same chance in a random survey, that's going to be a complex survey.
Yes. Yes, absolutely. Someone else has your hand up. Please unmute.
Hi. I think that maybe in addition to that, the survey questions are designed in a way that integrates multiple types of sort of answer types, like Likert scale plus others. Not only it's not limited only to Likert scale. Different types of questions and answer types are integrated into one survey. Maybe.
Yes, that's distinctly possible. Someone else has your hand up? Yes, unmute. Yeah.
Can I say something?
Yes, please.
I understand the complex survey data as is based on multi-stage sampling, so make it complex.
That is very common. Not technically required, but it is extremely common. All right. So thank you for answering, everybody. You're all right on the money here. So let's talk about this. In complex survey data, we do not assume a simple random sample, or SRS. The definition of a simple random sample is that each element in the population, and usually we mean people, but they use the word element to make it a little more general in case you're sampling non-humans as well, because that's possible. But each element in the population has an equal chance of being selected into the sample. In complex survey data, we are explicitly not doing that. Now, convenience sampling, we know that not everybody has the same probability of being selected into the sample, but in convenience sampling, we don't know the probability with which individuals are selected in the sample. In complex survey data, we are able to calculate that probability, and that is the major key. That's what's critically important, is that it's not equal among all elements of the population, and we are able to calculate what that probability is for each person who is brought into our sample. So that's what's important, and that information is contained in a sampling weight variable, which is just a column in your data set, and it's just a bunch of numbers. What's important about that bunch of numbers is if you added up every number in that column, you should get a very good estimate of the number of elements in your population. In other words, the sum of the sampling weight should be a good approximation of the total number of elements in the population. Now, how do you get this unequal probability of coming into the sample? Well, you have either strata or clustering, or both. You could have both of them. So let's talk about some other questions here. What is stratification? What is clustering? And why do we care about this stuff to begin with? All righty, let's open it up. Anybody care to answer any or all of these questions without looking at the next slide, please? Anybody want to be brave?
Yes, please.
Yes,
Let me start with the stratification.
yes.
Stratification is dividing the population into more homogeneous groups, which is considered the outcome response. So that means anytime the resulting outcome is different among the different stratum, then you have to consider stratifying your population into homogeneous groups. Thank you.
Yes. Yes, that's correct. Anybody want to answer either of the other two questions? Okay, so stratification, as he said, is basically breaking the population up into homogeneous groups, such that every element of the population belongs to one and only one strata, right? So you have your population and you break it up such that every element belongs to just one strata, and hopefully the elements in each strata are homogeneous or similar to one another. And if that stratification variable is related to your outcome variable, then it is definitely true that you will see a reduction in your standard errors. However, it is also true that, you know, the people who are designing and doing the collection of the data have absolutely no idea what you're going to choose as your outcome variable. So in reality, your outcome variable may or may not be related to the stratification variables. And typically it is variables. They're categorical, although sometimes they've taken a continuous variable such as age and made it categorical, you know, ages 0 through 5, 6 through 10, whatever it may be. And then maybe they use, I don't know, which state you live in or whatever else it is. And so you can have just this huge matrix of categorical variables, but every element of the population belongs to just one cell in that matrix. Okay. So we have an example here. I got this graphic from another web page. I didn't make this one up myself. And here we have stratified random sampling. So we have the red strata and the blue strata. And then the individuals who are circled are sampled into or brought into our sample here. This is different from cluster sampling. Cluster means we're just grabbing a big cluster of individuals. So for example, we might start off sampling with metropolitan statistical areas or MSAs, and then work our way down to a block, and then work our way down to a house, and then sample an individual within a single household. So that's that multi-stage aspect that was mentioned previously. That's very typical here. In this illustration, again, the red and blue represent the strata, but here we've just grabbed the three who are standing next to each other here and the three who are standing next to each other here to give you the idea that in the cluster, it typically is a geographic thing, that they're clustered together in geography or in space. And then we take something big like a metropolitan statistical unit, and that's called our primary sampling unit or PSU. And then we dig our way down through the secondary sampling unit or SSU, the tertiary sampling unit or TSU, and so on, until at long last we finally get a human being. But the major point here, and I'll answer your question in just a second, the major point here is that each stage of the sampling, we know what the probability is that this primary sampling unit, the secondary sampling unit, this tertiary sampling unit, this individual is brought into the sample. And at the end, what we do is multiply all those together to give us a sampling weight. Yes, your question, please.
So, what I understand is like in this.
Can you speak up, please?
Oh, okay. What I understand from this diagram is like in the one stage cluster sampling, we sample the other people in that cluster, right?
So in a one-stage cluster, it means that you're just taking a cluster of individuals, and everybody in that cluster is now part of your sample.
Okay, thank you.
And it doesn't matter how you have defined your clusters, but you take that cluster and everybody in that cluster is in there, and that's a one-stage cluster sample, yes. Okay, so let's go on and ask the important question, why does any of this matter? Why do you care about all this stuff? And the reason you care about it is math, all right? That's why you care about the math. You don't have to see the math, you don't have to do the math, but you have to know what's going on behind the scenes. The sampling weight is used in the calculation of any point estimate. A point estimate could be a mean, it could be a regression coefficient, anything that you are calculating. And so what's happening behind the scenes, whether you use SPSS via the point and click interface or via syntax, is that when you use complex samples and you've specified a sampling weight, SPSS actually uses a different formula for calculating, call it the mean, just for an example, uses a different formula for calculating the mean than it does when you just use the mean command or the descriptives command outside of complex samples. It's actually a different formula. And that's what you need to know, because you don't want to think, oh, well, it's complex survey data. The publishers of the data have already taken care of all this stuff. And so I can just analyze these data as if they were just any other data. That part's not true. There are special variables in the data set that you let SPSS know about. And based on what you tell SPSS, it goes and figures out what the right set of formulas are to use. And so if I had, for example, a one-stage cluster analysis, I would set up my plan file, and we'll get to plan files in just a second. I'd set it up differently than if I had a stratified clustered sample, and the math behind the two would be different. And you don't have to know what the math is. You don't have to worry about any of that stuff. The program will take care of all that for you. You just have to have clear communication between you and SPSS with regard to the way the data were collected. Okay, so the sampling weight is used in the calculation of the point estimate. Stratification and/or cluster variables are used in the calculation of the standard error. Now, I can't tell you how many times people have come to me and said, well, Christine, I just don't care about the standard error. I just need the point estimate and know whether or not it's statistically significant. And then I say, well, now you do care about the standard error, because the point estimate divided by the standard error is your test statistic. So there's no test of statistical significance without a standard error. That is critical. And you want that standard error to be calculated correctly. Of course you do. If you ignore this stuff, you could, but your results will only generalize to the sample, not to the population from which the sample was drawn. Now, I have actually seen a few cases where researchers were only interested in a sample, but in general, most of the time, what you want to do is generalize from this sample to the population. And in order to do that, you need to incorporate the sampling weight and the stratification and/or cluster variables. I always say and/or because you don't always have both. In our example, you're going to have both because you usually do have both. But you could have just stratification. The GIST data set that's actually collected at UCLA actually has stratified simple random samples. So they stratify and then do simple random sampling within each of the strata. So there you wouldn't have a cluster variable. There are one-stage cluster designs out there, so you would have a cluster variable and not a strata variable. You got to use whatever they give you to correct up your standard errors. All righty. Replicate weights are another way of doing what the PSU and strata variables do. In other words, they're another way of correcting the standard errors. And there's about a half a dozen different kinds of them. But as of the current version of SPSS, you can't use those in complex samples because they haven't incorporated that feature yet. So anyhow, if you're reading the documentation for your data set and it says that it's released with replicate weights, you're going to have to use different software. Okay, so I have a quick summary slide here of the important things to remember. We know that the sampling weight is used in the math to calculate your population estimate. Your clustering variables, stratification variable are used to correct up your standard errors. That's often called the variance estimate. And when you're looking through the documentation for your data set, there's always a section somewhere that talks about variance estimation. You want to look at that. Variance estimation is just a general term, but it will tell you what the design was and what variables you're looking for here. If you don't use your sampling weight, you can only generalize to your sample, not to the population. SPSS currently doesn't allow the use of replicate weights, but they do the same job as cluster and stratification variables do. All right, that was an introduction. Let's get down to some analyses, shall we? The example data set we're going to use in this workshop is called NHANES 2F. It is a shortened and cleaned up version of the NHANES 2 data. It's not actually available off of the NHANES website. It was an example data set used in other software, and I really liked it. So I just converted it over into SPSS because it's really good for teaching purposes. So let's talk about first things first here. There's really no going around it. You need to read the documentation for the data set that you want to use. You don't have to read all the documentation. It's typically more than 100 pages, and I'm not asking you to read it all. But you do need to read about the variables you're interested in. You do need to read about how the sample was collected and the population to which you can generalize. So for example, with NHANES, you cannot generalize your results to what they call institutionalized individuals. That includes folks who are currently in the military, folks who are in jails and prisons, folks who are in any sort of group quarters where they didn't have much of a say about being there. So there are limits to where you can generalize your results, and you want to know what those are so that you don't overstate anything. Let's see here. You need to, here's the link to the NHANES data if you want that. And then click on the survey and documentation tab. I think it was like kind of right in the middle at the top there. We're going to, on the next slide, figure out if SPSS Complex Samples is licensed on your installation. And then finally, have a look at the SPSS syntax guide for the procedures you want to use. To do that, open up, here's SPSS, click on Help, and click here. I already have it open, so I don't want to open it up a second time on mine, but that's what you want to do. And it is going to look like this. And we will look at this a little bit later on, but I don't want this to be mysterious to anybody, because this here is basically everything that is available to you. And this includes stuff that may not be available through the point and click interface, okay? When they make those types of interfaces, they necessarily avoid using all of the possible options because they don't want it to be overwhelming. They want it to be user-friendly, and so they include what most people use most of the time, but that means some things may not be there, but it's all here in the syntax guide, and I will show you how to use this later on. But you can scroll through this, you can expand sections and see, you know, what's available for each of the different subcommands that are available to you. All right, so how do you know if you have SPSS Complex Samples installed in your installation of SPSS? You run the show license command, and in a syntax window, so you file and either open or new, and then come down here to syntax. That's how you open up a new syntax window. If you've already got one, come here and you can open it up like this, and you type show license. You don't need an execute, you don't need anything else, just highlight it and run it. You do need the period though. SPSS uses a period as the end of command marker, so you definitely need the period. It's like a sentence in English, it always ends in a period. You're going to get a table that looks like this. It could be shorter than this. If you're currently affiliated with the University of California and you got your license through Software Central, then yours is going to look like this. And these are the different modules that are available to be licensed with SPSS. So what you're looking here is for this one here that says Complex Samples here. All right. One last quick note. There is a wait command in SPSS. It's not in the Complex Samples module, and it's used for frequency weights. There's actually there's more than three kinds of weights, but the three most common types of weights are frequency weights, sampling weights, or known as probability weights, and then analytic weights. The weight command is meant for frequency weights. We don't have those. Those are always whole numbers. And what they do is they expand your data set. Let us say that you had 3 variables and all of them were binary and you had 100 observations. Well, you can imagine that there's lots of rows that are exactly identical because there's only 3 variables and they're all binary. And so the frequency weight would tell SPSS how many times that particular row was replicated in the data set. It's just a way of shortening up the data set. Frequently used, commonly used when storage space was at a premium. You don't see it used so much anymore, but that's what it was for. That is not the situation we're in, so you leave that alone. Split file is a command that is frequently used when you want to break your output up by different groups, and that cannot be used with complex samples. When we get to breaking our analysis up by groups, we will be using either a subpop or a domain subcommand, and I've got a whole section on that coming up. But I just want you to realize that these commands with which you may be familiar, maybe used frequently, they can't be used with complex samples. Okay, any questions up to this point? Okay, so we made it obvious, made it clear that there needs to be clear communication between you and SPSS regarding the elements, the sampling design elements in your data set. The sampling weight, the PSU variable, and the stratification variable. The way you're going to do that is by creating what SPSS calls a plan file. You have to have this because that is one of the few required subcommands for every CS command that there is. So you have to have that. You can create this using either point and click or syntax. I personally do the point and click and then I save the syntax because knowing what the syntax is before I do this, little bit more than I retain in my memory, but the point and click interface is pretty straightforward. So let's talk about syntax in the output. I don't know why, but somewhere, I don't know if it was version 29, version 28, they changed the default so that the syntax doesn't echo in the output file. And that is like seriously annoying. So you want to have your syntax shown in the output file, whether you wrote the syntax or you use the point and click interface. And so to talk SPSS into doing that, you are going to click on Edit, Options, and then go to the Viewer tab. So you're going to come here to Edit, come down here to Options, and then you're going to come over here to the Viewer tab. When you're here, look down here and you want to check mark here. Okay, and that will put all of your commands in your output file where you can simply copy and paste them into your syntax file when you have an analysis that you would like to retain. So I have a cute little graphic here to remind you of how to do that if you're going to do this sometime later. All right, let's open up the data set. Okay, so we've got a get file command. You open up the data set the same way you always open up a data set. You can click on file open if you want, or if you want to put it in your syntax. I usually put the get file in my syntax so that I remember what data file is associated with the syntax and I remember where the data file is. So I do that. There's your command here. You can use single or double quotes. The period must be outside of the final quote. And for reasons I have never understood, you do have to have the SAV extension here. So SAV is the extension for an SPSS data file. So here's the name of the file, period, SAV, close the quote, and then the period to say this is the end of the command. All right, your path directory will look different from this. This is just where it's located on my computer, so you're just going to look different. Now I need the following information before I move forward. I need the name of my three variables, my sampling weight variable, my stratification variable, and my cluster variable. I have to know the names of the variables. I have to know what they're called in the data set so that I can find them and put them in the right place. So I've got this information. And when you're doing this, you definitely want to make sure that you've got this information at the ready before you start. Okay, we're going to point and click our way to the command file, or excuse me, to the plan file. I'm going to click on Analyze, Complex Samples, and Prepare for the Analysis. So I'm here. I'm going to click on Analyze. I'm going to come down here to Complex Samples, and then I'm going to click here. Okay, now I've already got mine set up, and if I do it again, it's going to give me funny error messages that I don't want to confuse anybody with, so I'm not going to do this. But if you were doing this, this is where you're going to click, and then you'll go through the prompts. And I have the prompts screen captured here. So this is the default, is to create a plan file. Okay, that's exactly what you want to do. And you're going to click on Next. Okay, step one, we got it pretty easy. Step two, you're going to give the name of the plan file here. I called mine NHANES2F_plan so that I know the plan file is associated with this data set. That's how I keep my files organized and I keep myself straight. You can call it whatever you want, but that's the way that I do it. And then I click on Save. All right, here's where we have to know all of our variable names. So here's your list of variables. You click over the strata variable, you click over the PSU variable, and you click over the sampling weight variable. All right, so you got those three variables in here, and then you go ahead and click on Next. All right, so we're here, and we have to have a quick conversation about with replacement and without replacement sampling. The truth is that for every data set out there, they use without replacement sampling, which means that once I have been selected in the sample, I can't be selected in the sample again. I'm not replaced in the population so that I have another probability, another chance of being selected in the sample. In other words, I don't get represented in the data set twice. I only get represented once. However, if you think about that, that means once I've been sampled into the data set, into the sample, all of your probabilities for being selected in the sample change because now the number of elements in the population has changed just by a little bit, just by a little bit, but they have changed. But what happens in reality is that we run these analyses as if we did with replacement sampling because the math is a lot easier and there's so little benefit to changing the probabilities and doing all of that over and over again that it's just not worth it. So even though in reality we do run the analysis without replacement, we're going to analyze as if we did it with replacement. Now, what's critical here is that you uncheck this use finite population correction. If you don't have an FPC variable in your data set, you're going to have a problem because the next window will ask you for that variable name. And if it's not in your data set, now you got a problem. So uncheck this here. So this is the only thing checked here. And then we're going to click on Next. So we're going to look at this and it's okay that we don't have a label. This is our strata ID. This is our cluster ID. This is our weight. We don't have a PSU variable and we are doing with replacement, at least for the math. And we go ahead and click on Next. So we come here and this is the final thing. And we're asked, do you want to save your plan file or paste the syntax? Well, we already get the syntax for free because before we started this whole thing, what we did was asked SPSS to echo the syntax in our output. So we don't need to paste it. We've already got that. So save your plan file, because in every call to any complex sample procedure, you have to specify the plan file. So you have to have it saved somewhere. And so we're going to go ahead and save it. So you go ahead and click on finish. When you do that, here is the echo of what we did. This warning will always appear. Okay, it does not mean that you have done anything wrong. It will always be there. And what it's trying to warn you is that SPSS is not checking the consistency of the working data file and the plan file. So in other words, if you specify the wrong plan file with your current data file, SPSS ain't gonna know that. Unless, of course, you say, hey, there's Strata ID and PSU ID, and they're not in your data set, and then SPSS will issue some sort of error here. But what it's saying is that it doesn't make a connection between the plan file and the data file. So that's up to you to do it. That's why I named that way with the underscore plan, so that I don't make that mistake. But that's what it's trying to tell you. Okay. Oh, whoops. And then here is just an echo of what we have already seen. Okay. We got through all of that. Do we have any questions at this point? Okay. All right. Let's talk about what you should do with your data before you start the analysis. It may seem like kind of a strange thing, but you really should get the mean, minimum, and maximum of your sampling weight variable. And I will explain that on the next slide. You should check for numbers of missing cases. Why would you do that? Because you want to know if there are some variables that you were hoping to use that have crazy amounts of missing data. And I have seen that in some data sets. I have seen data sets where like 90% of the cases were missing. Well, you want to know that before you start doing anything, because 90% missing, like maybe I'm not going to be using that variable. You want to ensure that the sampling weight, the cluster, and the stratification variables don't have missing values. This is the one time that I will say if there's a missing on one of those variables, you can just delete the row out of the data set, because the row can never get used. I don't think I've ever seen a case where I've had a missing on a cluster variable or on a stratification variable, but I did see one data set that had missing on the sampling weight variable. And I actually had to contact the publishers of the data and ask about that. And they said that what happened was that they had inadvertently sampled individuals into the data set that were not members of the target population. And so they had given them a missing sampling weight. Okay. But that's why they did it. But in general, you should never have missing on those three variables. And then you need to do any data management tasks. So for example, if you're going to create new variables, you're going to recode variables, definitely make sure that you label your variables, add value labels as appropriate, document what you have done. All righty, let's look at the sampling weight variable. Outside of complex samples, you can usually shorten the command names and stuff. And so I do. In complex samples, you can't do that, which I find to be like seriously annoying, but whatever. This is short for descriptives. This is short for variables. And this is our sampling weight variable. I can see that I have no missing data here. The minimum is 2,000. The maximum is 79,634. And the mean is 11,320. Okay, why do I care about this? Every once in a while, you will encounter a data set that has a normalized sampling weight, and you will know immediately if it's normalized because the mean will be very, very close to 1, and the minimum and maximum will not be far from 1. Okay, the standard deviation will be really small. And so you will have some cases where the sampling weight is actually less than 1, which I always think is kind of weird, because how can you represent less than 1 unit in a population? But it's a math thing. When they standardize this, there are different reasons why they might do it, but that's a kind of a different sort of issue. And I just need to know if it got standardized, because then I might have some different options going forward. So you do want to have a quick look at that. And then here's the histogram. Here's the graph, histogram, final weight. Here's the histogram here. I look at this because every once in a while, outlier weights can cause some estimation problems. So if I start hitting estimation problems when I'm using the weights versus when I'm not using the weights, then this is one of the places where I'm going to start to wonder if my problem is caused by some weird outliers. In this data set, this isn't enough of an outlier to cause any problems, but it's just something that you want to know about the weight variable in case you do encounter any problems. All right, with that, we're going to move into the descriptives for continuous variables. Do we have any questions at this point, please? Okay, so we're going to use the CS descriptives command. Hey, it is very much like the descriptives command that you have outside of complex samples, and except for fewer options, I gotta say. The only thing is that you have to use a mean, a sum, or a ratio subcommand with this procedure. And of course the plan. I'm just going to assume that the plan subcommand is always there, but you do have to request a mean, a sum, or a ratio, and we'll go through examples of each of these. Okay, so we're going to start off nice and easy. We're going to get the mean of the variable age. Okay, age is a continuous variable in our data set. So we have the CS descriptives command. Our first subcommand. The subcommands can be in any order. I always put the plan subcommand first because it is required. And this is something that you simply copy and paste over and over and over again. It's easy enough to do. Notice though that the extension here is CSA plan. There are different kinds of extensions here, so just be careful. This is CSA plan here. We have a summary subcommand here. The variables, I can list more than one variable, but for now I'm starting off easy. Let's just do age. I have my mean subcommand, and then I have statistics, and this is what I'm asking SPSS to show me in my output. So I want the standard error. I want the count. This is the raw count, the population size or the weighted count, and then a 95% confidence interval. Why do I want the weighted count and the unweighted count? I want the unweighted count because this is how I can tell if there's missing around here, because I know that there's 10,337 observations in my data set. And so if this number comes down, I know that I have some missing. And then this should be the estimated population size when the unweighted count is this. So the average age of the individuals estimated in the US at the point in time in which these data were collected was 42.24 years. The standard error is nice and small, of course, because that's a large N here. And the confidence interval, of course, is nice and tight because the standard error is small. So we can have some missing values. If you look at the variable copper, there are some missing values. The syntax is exactly the same as on the last slide, except for I changed age to copper, and we see that we have some missing data here. Hence, the population size estimate is a little bit lower. Okay. If we look at I believe this is hematocrit, it's a thing in your blood here. We're back up to our total sample size. So what happens here if you put all these variables in the same call? Turns out you have options, which is always a good thing. So I've listed all three variables here. I've got my mean subcommand, the statistics that I want to see in my output, and we can see our unweighted count here. Notice our estimated population size is moving around as we have missing data here. So there are different ways to handle the missing data. The default there is what they call scope equals analysis. There's a understood missing subcommand here, and this is the scope equals analysis, and that gives you this. And so by analysis, what it means is basically it ran this as one run, this is a second run, and this hematocrit as the third run. But you can do a listwise deletion if you wish, and that means that the only rows of data used in the analysis are the rows that have complete data for all three of the variables. And notice that the means for age and hematocrit are slightly different, right? Because we're using fewer rows of data in this calculation. Okay, a quick side note about missing data. Please do not delete all the cases with missing data to create a data set that has only complete cases. In general, you may not delete cases out of a weighted data set because, as I said before, if you sum down the sampling weight variable, you should get a very good estimate of the population, right? Well, if you start taking out rows of data because they're missing on copper or they're missing on some other variable, now when you sum down the row, you don't sum to the population. The other problem with that is now I have an undefined population to which to generalize my results. So let us say that we had, you know, everybody in the United States as our population. Now, if I take out all these rows with missing data, missing on any of the variables that I care about, now I have some undefined population where, you know, they're only the people who would answer all the questions. I don't know how to define that population. It totally messes up population inference. So if you've got missing data, leave it alone, right? You have other imputation options to handle missing data if you need to go that route, but just deleting those cases isn't a good way to go. All right, let's talk about a design effect because we're going to ask for a design effect coming up in the next slide. A design effect, excuse me, is the ratio of two variances. In the numerator, we have the variance of the estimate from the current sample, which includes using all of the design elements, the weight variable, PSU, stratification, all that. The denominator is the variance from a hypothetical sample of exactly the same size, but was drawn as a simple random sample. And this is going to indicate how efficient your sample is compared to a simple random sample of the same size. So if you think about that for just a second here, the design effect, if it's less than 1, your sample is more efficient. And if it's greater than 1, your sample is less efficient. In general, your design effect will be greater than 1. And typically the culprit there is the clustering. The clustering tends to really inflate the design effect. The good news is for the design effect, it's usually something that you only have to report, and it is what it is, okay? There is no need to get up in arms if it's above some value or anything else. It just is what it is. It's, like I said, a quantity that is typically reported. You don't interpret it. You don't worry about it. It's just a thing. And I just want it not to be a complete mystery to people. It's a ratio of the variance of your sample compared to a hypothetical simple random sample of the same size. Getting this design effect means you add the DEFF option to the statistics subcommand here. We used the 3 variables that we had previously, and we see a new column in our output here. And again, not surprised that they're above 1. I have seen them 10, 20, I've seen 50 before. So again, I don't really care what the number is. It's just sometimes I have to report it, and that's how I get it. So let's try using some of the other subcommands that are available and required with CS descriptives. Let's look at sum. I typically don't see a lot of instances in which I need to get the sum of a variable here. So my example here might be a bit of a stretch for folks, but I summed the variable female. So the variable female is a binary variable. It is coded 1 if you identify as a female and 0 if you do not. Okay, that's just the definition. It's just a binary variable. And so what happens if I take the sum of the variable female? Anybody? What happens if I take the sum of a binary variable? Oh, come on, this is a soft pitch, guys. Yes, Ben, please.
It's the number of females in the population.
Yes, thank you. Yep, it really is that easy. Yes. And so here is the estimated number of females in the population. And if you do a little bit of math in your head, you'll see it's probably slightly more than half of the population identifies as female. Okay, so there's that. Let's look at the ratio of copper to hemocrit in medical science. Does that make sense? I don't know. I just had to have an example. So we have the ratio subcommand. You do have to spell out numerator and indicate what the numerator is. You have to spell out denominator and indicate what the denominator is. Okay, and both of the variables have to be on the summary subcommand. So here is our ratio estimate and the standard error. Notice that this is less than the total N because we still have missing on copper. All righty. So let's ask a question here. How could you get the ratio of females to males? If you wanted to do that, how could you do that? Think about that for a second and then give me an answer. There's no trick question here. Okay, if you're thinking this is going to be tricky, it isn't. It's really especially when you see the answers and like, oh, well, that's really obvious.
Well, let me try.
Yes, please.
Dividing the number of females to the number of males.
Yes, but if I don't have the variable male in my data set, what am I going to do? Well, I'm going to create it, of course, right?
You can
Yeah, I think you can create
actually.
the
Yes.
female.
Yes, and there's many different ways that you could create it. All right, so here we go. This is one way, okay? There are many different ways you could do this. I used the recode command and I said 0 equals 1, 1 equals 0, and I put it into a new variable called male. And then I quickly checked this to make sure that that is true by doing a cross tab with the variable female and the variable male, just to make sure that I didn't screw anything up or, nothing silly happened. And now, what you're going to do is use your ratio and you'll put female here and male here. And then you will see this, and this corresponds to what we saw before where there are slightly more females in the population than males. Okay, any questions about this?
Population size is so large because why is this so? Because it's representing the entire the real numbers?
This population size
Yeah, it's so
is
large.
the estimate of the non-institutionalized US population at the time that the data were collected.
So this is kind of actual number then?
Yes,
It's not the sample, the number, right? It's the entire population.
this is the weighted population size. This is the unweighted count. So there are actually 10,337 observations in the data set. And that is a sample from a population of this size.
Okay, thank you.
Yes. All right. What if we wanted to ask if the mean of a variable is different from a value that we specify? We can use the t-test option on the mean sub command. So I have my variable hemocrit here. I have my mean sub command. I have the t-test option, and I just picked the number 40. Okay, this is where your substantive knowledge of the data that you are using would come into play, and you would specify this number based on your theory, right? And so here is this mean here, the lower and upper confidence interval. All of this is what we typically see in our output. Here is the test value, which I specified right here. Here is the t-test statistics on 31 degrees of freedom. We will get to why it's 31 degrees of freedom shortly. And then here is our p-value. Since it is less than 0.05, we are going to conclude that this 41.98 is different from 40. Okay, I don't know how often people would do that, but if you need to do that, this is how you would do it. Let's move on here to descriptives with a binary variable. You can do descriptives, use the CS descriptives command with a binary variable. And when you take the mean of a binary variable, you get the
frequency.
Get the proportion. Yes,
Or
the proportion of ones. Yes. And again, we see that this is just above half. So again, we have seen that we have slightly more females in this population than the males. So this is a proportion. Anyhow, these are things you can do with the CS descriptives command. The other descriptives command in complex samples is CS tabulate, and it creates one-way frequency tables and two-way crosstabs. It does not create multi-way crosstabs, sorry, only two-way. You need to have the plan subcommand as always and a table subcommand. You probably do want some other subcommands to control your output. So let's do frequencies for the variable female. Notice we're now using CS tabulate here, and I just have my two required subcommands. The defaults here are a cell subcommand giving me the population size and a statistics subcommand giving me the standard error. So my output here is the estimated number of males, the estimated number of females, the standard errors around those, and then the total. So if we add some other subcommands, we certainly can. Here are cells, we added population size and table percent, and then we added count here. Notice though that when I added count here, my standard error went away. It's the default when there's no statistics subcommand, but when I add that and put something else here, now that default is gone. If I want the standard error, I need to add it back in here. And then here is your table percent here. Let's see here. I think I've already covered that. Okay. We're actually going to come up to a break sometime soon here, so hold on for just a little bit here. We can test for homogeneity of proportions if you would like here, here is your CS tabulate command. All of this is exactly what I had previously. I added a test subcommand and I wrote homogeneity on that. And this is a test for the homogeneity of the proportions. And this is what your output's going to look like. So we saw this output here in the previous slide. This is your table percents here. And this is the new table added by the test subcommand here. And what you want to look at here is this adjusted F. This is an unadjusted chi-square. You want the adjusted F that's adjusted for the sampling plan here. And whether you use a Pearson or a likelihood ratio, you get the same number of degrees of freedom and the same conclusion here. Okay, so that's available to you. If you want a cross tab here, you put two variables separated by the SPSS keyword by right here. So I've got female by the variable rural. So it's 0 if it's urban and 1 if it's rural here. And this is the number of males living in urban areas, the number of males in rural areas, and the same thing for your females here. Okay, let's go ahead and add some options here. I put in cells and statistics. You can have row percent, you can have column percent, you can have table percent. I don't recommend putting all of these in the same call if you don't need all of them, just because it generates an awful lot of output. And my table looks very small here because in point of fact, there's lots of output. And so you can drive yourself crazy in these tables, but here is your male. And then here is in rural, here's your female. And then here's rural. And then here's your total. Lots and lots of output there. You can make multiple two-way tables at once. The trick is to put the variables here by in the single variable here. So what you're going to get here is female by rural and this variable health by rural. Okay, and so that's what you're going to get. And yes, there's lots of output. Right? This is how I ended up with so many slides because I'm like, wow, there's lots of output. That's why I squished them all onto as few slides as possible, but that's what happens here. You know, there's lots of output here. You can ask for a chi-square test of independence, and that is on the test subcommand, and you use independence. You must have table percent on the cells subcommand here, and you must have yes, and then I put expected here because typically you would check the expected number of observations in each cell. I don't really worry about that here, but you could possibly have fewer if you had a subpopulation, and we're getting to subpopulations really soon. So here are our output tables here. This is your two-way table here. And then here is your chi-square test of independence. Again, you want to look at your adjusted F. And so here it says that there is a relationship between the variable female and the variable rural. All right, so we are going to have some time for some exercises if you would like. The data set is on the web page, so you can download that and then you can give these things a try. Or if not, we can just take a break. Since we're running a little bit low on time already, let's just take a 5-minute break. So we'll come back at 15 minutes past the hour. If you have any questions for me, you are welcome to ask them now while others are taking a break. I'll stay here. Yes.
Wait. Get the do you know silicomas?
I'm sorry, one more time. I'm sorry, can you repeat your question, please?
I'm
Okay.
not sure they're actually asking anything.
Okay, all right, so we'll come back at 15 minutes past the hour.
Hello, Christine.
Yes.
Hi, quick question. For the categorical variables, like on the Haynes site, you can pull down the data, but is there any way to pull down the value labels? In the past, I've done that, had to manually enter them. Is there any way to pull those down, like with the data set?
It should not be with the data. You'll get the data usually as a text file or something, and then you'll get either the SAS or the Stata or the SPSS code to read it in, and that should be where you'll find the variable labels and the value labels.
Okay, so the data sets usually come down as a SAS XPT file. So all I've ever,
Okay, then
yeah.
it should be included in the SAS XPT file.
I've never found those in there. Does a proc format in SAS automatically write those to the XPT, or is it in another format?
I seem to remember getting very long SAS files that contained the formats when I've done it. But no, you are not supposed to have to type all that in yourself. That should be distributed with the data. And like I said, that should be for whatever format you get. Although it is true, at least now, that both SPSS and Stata will read a SAS XPT file.
Okay, I'll take another look on the enhanced site. I was never able to quite locate them on there, but I'll take another.
If you continue to have a problem with that, email me directly, and I will bash around and see what's going on, because I know that they distribute that. I once contacted them and told them they had a typo in one. So no, they do distribute that.
Awesome. Thank you so much. I'm enjoying this so much, and I will do that. I'll take another look, and then if I need to reach out, I will. Appreciate that.
Okay, sure. Yeah, thank you very much. Okay, it's a quarter past the hour. Let's talk about subpopulations. All right, this is one of the places where we're going to have a difference between the analysis of experimental data or unweighted data and complex survey data. As we've already said, with complex survey data, you almost never delete any cases from the data set, even if you're never going to use them in any of your analyses. Instead, what you're going to do is specify the cases you want to use on either a subpop or a domain subcommand in the procedure that you're using. What's going to happen is that the cases that you want included in your analysis will be used in the calculation of your point estimate, but the all the cases will be used in the estimate of the standard error. And that's the correct way to do it. I'm not going to go into all the theory behind that right now, but that's another reason that you can't go deleting cases out of your weighted data set, because they're needed for the calculation of the standard errors. So why do I say that there's a subpop and a domain subcommand? Because for reasons I cannot tell you, SPSS uses a subpop subcommand, try saying that 3 times fast, with descriptive procedures and a domain subcommand with regression procedures. And so they essentially do the same thing. They don't work exactly the same way, but we're going to get examples of both. But that's how you analyze just certain parts of your data. Right. So if you were only interested in females, or females over the age of 50, or females over the age of 50 who live in California, that is how you would go about doing that. So let's start off with a simple example. This is no subpopulation. We're using all the data. And I say, just remember this analysis, because we did this early on. We got the mean age here, and we remember our 42.24. Now let's analyze a subpopulation here, and we're going to subpop by female. So we have a subpop subcommand. We do need to say table equals female. I will get to this display equals layered in just a minute, and we have to have the mean subcommand here. So here is our univariate statistics. This is the overall population. And then here are our subpop. Here we have the mean for males and the mean for females here. Okay, and we have 2 values here because the variable female has 2 values. Layered means it got put in the same table as layers. If you want to have separate tables, then it's display equals separate rather than layered. Everything else about my syntax stayed the same. And now instead of having 2 tables, I have 3 tables. Okay, so this is the univariate for everybody. Here is for female equals male and female equals female here. So different ways of doing the same thing here. You can have different variables here. You can have actually a goodly number here. You separate them by the keyword by. So this is health by female. So your output here is going to have the average copper for each combination of the variable health and female. All right. So there's 5 here, 2 here. That should be about 10. Right. And so this is our overall estimate of the value of copper. And then when health is poor and male, health is poor and female, and so forth and so on here. If you had switched, if you had said female by health, your table would have contained the same information. It just would have been organized a little bit differently here. Okay. And then you can ask for whatever you want here. I just left it at the mean and standard error because I already have a lot of output here. You can add up to 17 variables in your subpop here. I don't recommend doing something like that. I don't know why you would need something like that, but just don't go completely crazy because you will have lots of output here. So I did female by race by region. Okay, and here is part 1 of the output. I cut the table in half because it wouldn't fit on my slide. Here's the other half of the table. Again, it goes down lots and lots. Typically here I have, see here I put in, I needed the count. I put in the count because when I do this, I want to look at this and make sure some of these numbers don't run down too small. So here, despite the population size here, I have a raw N of 5. I have a raw N of 6. I have a raw N of 8. Those numbers get to be awfully small, and these numbers are still fairly large, and that's the effect of your weighting. But I need to know if these numbers are running down a little too low for comfort here. Where your comfort level is up to you. But especially when I subpop, I really do want to pay attention to my unweighted count. Let's see here. We can use subpopulations for CS tabulate here. And so we've got our standard syntax here, and then we used a subpop subcommand, and we said table equals rural, and then here we go. So there we go, and that's part 1 here, and then here is part 2, and then part 3, because again, this was a really long table. So this is your overall table. Here are your subpopulation tables. Here is rural, and then here is rural 1. So lots of output. Again, pay attention to what options you really want, because you don't want an overwhelming table either for you or your audience. If you're just going to put this table in a presentation or something, you don't want to drown people in numbers. You cannot get a chi-square test with a subpopulation. I'm sorry about that. I kind of wish that wasn't true, but it is. You get your output here, but you get this warning here. The only exception to that is if your subpopulation variable is your stratification variable. So I don't see that too often here. In general, stratification variables in complex survey data sets created here in the United States are a crazy mix of all sorts of things. The other thing that I should say about that is that it is often the case that not all the levels of a variable are released to the public. So they may release a variable that's coded male, female, but the variable that they used may have had many more categories. Or they release a variable called region, and it's got 4 regions, but the variable that they used had 10 or 12 levels. And they do that to get precision, but if they released the original variable, it would probably be too revealing about who was in the sample. And so they release a more aggregated version of the variable to the public. And so stratification variable is often something you cannot recreate with the variables that are in your data set that is available to the public. Here's part 2 of our output here. Just another example, getting a sum here. I moved the subpop subcommand up just to show you that you could do it and like your computer won't explode or anything here. All right, any questions on that before we move into linear regression? All righty. So the CSGLM command is used to run linear regression. And the key here is that you can only use continuous outcomes with GLM. All right, so general linear model, not generalized linear model, but general linear model. In other words, linear regression. It has a lot of the same features as the plain old GLM command used for your unweighted data. Your outcome variable has to be continuous. And just as a point of clarification, a count is typically not a continuous variable. So just kind of be aware of that. And it's helpful if the outcome variable is approximately normally distributed. Now, SPSS isn't going to give you a weighted histogram or anything like that. So it's hard to know if the variable is going to be approximately normally distributed. And there is no assumption about the distribution of your outcome variable. Excuse me, the assumption has to do with the distribution of the residuals. But it is true that if the outcome variable has a really non-normal distribution, it may be more and more difficult to meet all of the assumptions of a linear regression. And in particular, what I worry about is violating the assumption of homogeneity of variance. If I violate normality of the residuals, you know what? I'm sure it won't be the worst thing that happens to me today. But I don't want to violate homogeneity of variance, because if I do that, my my standard errors get miscalculated, and that miscalculation is proportional to the extent of the violation of the assumption. So I don't want to do that. Okay, let's ask a question here. What do you call a linear regression with a single dichotomous predictor? Do not look at the next slide to answer the question. What is that?
Logistic.
Predictor, not outcome. Your predictor is dichotomous. Your outcome is still continuous. What do you call that?
ANOVA. Oh, a t-test.
T-test. Yes, it's a t-test. Very good. It's a t-test. And why do you care? Because there's no CST test command. And so if you find yourself in the situation where you want to run a t-test, you're going to use CSGLM. Okay, so when we have an example of that in the next slide, but I do need to go over some subcommands for regression models. These are the same across the 3 regression commands that we are going to cover today. Yeah, we're going to cover all of this. It's going to be a tight squeeze, but we're going to do it. CSGLM, CS logistic, and CS ordinal. Subcommands that are the same are domain, intercept, joint probability, which we don't have to use because that's for a different sampling plan. Missing, the plan file, of course it's the same, right? The out file and the test subcommands. They have a similar model and save subcommands across these different types of regressions. So let's go ahead and do this. We're going to use copper as our continuous outcome variable, and our predictor is going to be female. On this command here, we see CSGLM, our outcome variable, the SPSS keyword by. This means that a categorical predictor is going to follow, and that is the variable female. Later on, we will have examples with the SPSS keyword with, which means continuous predictors will follow. If you are very fluent in your SPSS syntax, you can say, well, this is coded 0-1, so I could have used with here, and you are correct. But since I'm going to use EM means later on, I'm going with by. Here's my plan subcommand. It has not changed throughout this entire workshop, and it isn't going to. Model has my predictor variables. I only have one predictor, and it is female. Statistics. I ask for the parameter. CI interval is your 95% confidence interval and your test statistic. The default is to give you unadjusted tests. I don't know why that's the default. I always want the adjusted test, adjusted for the sampling plan. And so that's why this test type equals adjusted F is here. Here is your regression output. There's lots of it. I stuffed it all onto one slide. So unweighted cases, this is your unweighted N. This invalid here is another way of saying missing. And so your non-missing and your missing summed together should give you the total number of cases or rows in your data set. Here's your estimated population size based on the valid N here. Here we need to talk about what's going on here. This units is PSU, or primary sampling units. That's why it's called units. We've been calling it clusters, same thing. We have 62 clusters in our data set. We have 31 strata. This number here is always calculated as number of PSUs minus number of strata. So that's why it's 31, because 62 minus 31 really is 31. So we'll be seeing this 31 coming up over and over again here. Here it is as our denominator degrees of freedom right here. let's see here, we have our factor information, factor because it's called a factor variable or the categorical predictor. We have 48.3% males and 51.7% females here. We have an R squared. This is what we would call a population R squared, or you might know as an adjusted R squared. Here is your test of model effects here. You always have a 1 degree of freedom test for each of your predictors. The model only has 1 degree of freedom because there's only one predictor. This DF2 is this 31 here. This is numerator, excuse me, put that. Numerator degrees of freedom, denominator degrees of freedom, adjusted wald test, and your p-values are over here. I had to ask for the parameter estimates. Here is your intercept, your coefficient for males and females are your reference group. Remember, in SPSS is always the highest numbered group in the predictor variable is the reference group. There's no way to change that in syntax. If you want to change it, you have to recode the variable. If you go ahead and recode the variable, please put on value labels so you remember what is what. But anyhow, here is this. We didn't ask for the standard error in this output, but this number divided by the standard error gives you this. This 31 comes from right here, and here are your p-values. All right. That should be familiar to most people. Okay, it's not terribly different from an unweighted analysis, and the interpretation is exactly the same. Any questions? Okay. We talked about how, yes.
Yeah, how do we interpret the coefficient? Negative, can you go back to, negative 26.23.
Right, so it'll be
It's
easier
just
to see when I get down to the EM mean subcommands here. But this is the estimated mean of copper for females, and this is the difference between females and males. Males versus females, because female is the reference group. So this is a mean, and this is the difference between the means for the two groups. And that's true only because we have no other predictors in the model. But this is exactly the same interpretation that you would have for an unweighted model. Does that make sense?
So male has a higher level of serum copper than female?
The females are higher than the males because the males have the negative. It's a negative. You subtract.
So female 0 here is a male instead of a
Yes.
female. Okay, I just
Yes.
confused. Okay.
Sorry. Yes. Yes. Female equals 1 is female. Female equals 0 is male. Or not female, technically. Yes, that's correct. We discussed this, so we've got this. The EM mean subcommand, if you've used it in other procedures, it's very similar here. I have exactly the same command. I've just added the EM mean subcommand tables. I have female, and then I used compare, which is just going to give me some redundant output. And the only thing with this, in the output, you get a t-test statistic, and then in the new output, you'll get an f-test statistic. On a 1 degree of freedom test, t squared is f, and that's all that this is. So just to show you that you're actually getting exactly the same output here. So you have the same output. All of this is the same. I just didn't repeat it because it's already long enough. And so here you recognize this 137.4, and then this is 111.13. The difference between that is that 26.26. That's this number right here is the difference in the means, right? So if you subtracted these numbers, you would get this. The only thing SPSS is bringing to the table here is that it's going to calculate the standard error for you, and you need that in order to get your WALD test. This 613 here is this 24.774 squared is that F value there. All right. And then this is just the overall test, which is redundant with what's in this table here. Okay. But my only point here is that EM means is available in this procedure, and it can be very helpful for discussing your results with your audience. So if you are talking with your audience and they're wondering, well, I don't know what this stuff means, you can have this at the ready and say, well, these are the means, and you just subtract them. That's the coefficient showing that males have a lower mean copper than females, and that difference is statistically significant. And sometimes showing this kind of thing is more informative to your audience than showing them this. Okay. So there's compare and contrast options here. The contrast option has the standard options that you see elsewhere in SPSS. There's deviation, there's Helmert, there's reverse Helmert, there's simple, there's all of those kinds of contrast options are available here if they are helpful to you. And this is just the output from EM means. Again, all of the rest of the output is exactly the same here. This is different here because we used the deviation contrast here. But it's, you know, whatever you want to do. I'm just showing you options that are available to you here. There's another way to specify variables on the EM means subcommand, and I changed my model here. Now I've got my outcome is still copper by, we have female, I've added diabetes, which is a 0, 1 variable, 1 if you have diabetes, 0 if you do not, the SPSS keyword width, and the continuous predictor age. I've added, I've included all of those predictors on the model subcommand, and then I added this interaction term. So we have an interaction between female and diabetes. And then on my EM means subcommand, I have female by diabetes, and I'm going to compare the diabetes group. All right, again, lots of output here. We do have missing cases here. So our population size is estimated to be a little bit smaller because of the missing here, but this 31 degrees of freedom is still here. We have the mean of our outcome variable and now a row for our covariates. If we had more covariates, they would all be listed here with their means. The factor information for all of the categorical predictors, looking at our percents. This can be useful because you see here that the number of cases coded 1 in the diabetes variable is fairly small, right? Only 3.4%. We have our adjusted R squared here, and now our table with our degrees of freedom. These are all 1 degree of freedom tests because these are binary and this is continuous. The degrees of freedom are not whole numbers because of the complex weighting, but reviewers don't expect whole numbers. So none of them are surprised when you report 3.1 degrees of freedom. You know, in most cases, that would be really strange. Here, it's kind of expected. All right, so that's what we get here. And then here are our coefficients. And this should look like, you know, output from any regression or GLM command that you've run in SPSS. Here's your intercept. the highest level of a variable is used as the reference group. And then again, you get the one coefficient for this because it's a categorical by categorical interaction, and the overall interaction term is statistically significant. This is the output from the margins command. And here we have the mean of our outcome variable for each of these values, holding our covariate at its mean here. The mean is a little bit different than what we saw for the entire population, because remember, we have some missing cases here. And then here we have for males and for females, looking at diabetic versus not diabetic here. So it is statistically significant for when you're looking only at males, and it is not statistically significant when you're only looking at females. And then here is your overall test statistics. Okay, you can use multiple EM means subcommands if you would like. That is also completely legitimate. I scaled the model back just to have two main effects here. And so here is our model information here. And then this is the output. These are your parameter estimates. The first table for the EM means for female, and then the second table, the EM means for diabetes. All right, you can specify a value of the covariate that you would like to have it evaluated at. You don't have to take it right at the mean. I've changed the model again. I changed to a different outcome just to show you that you can, and there's no rhyme or reason here. This is your systolic blood pressure here, predicted by the categorical variable female with the continuous variable height. And so we have female, there's a typo here. It should be female height by female height here. And then we are holding height at 150 and 160. Alrighty, so we have that. And let's see here. And then here are your parameter estimates. And then here you can see that we have height at 150 and height at 160. Okay, any questions?
So each time when we change the command, we have to create a plan file. I'm not sure why we have to create a plan file each time.
You don't. You just have to specify it. It's the same plan file. There's only one plan file.
Oh, it's the same thing all the time. I see.
It's the
Okay.
same thing all the time, every single time. You're just telling SPSS where it is. Yep.
So we can so we cannot omit after doing the first time. Second time we cannot omit it.
Nope. You are going to use it every single time you run a CS command. You must have a plan subcommand, and you have to provide the plan file that's associated with that specific data set. Yes.
Okay, I see. Thank you.
Mm-hmm. So let's see here. We have female diabetes, age, and female by diabetes. Here I did it with an asterisk, which is what I have been doing previously. We're familiar with this output. Here's some more output. Here's more output. But what I wanted to show you is that now I can do the same thing with the SPSS keyword by. The important thing to keep in mind here is that when you say by on the model statement, it's different than by on the command itself. Here, by means categorical predictors are going to follow. On the model statement, by means make an interaction term female by diabetes. Is that clear? Okay, I hope it is, and the output's exactly the same. If you want to create a squared term, you can. Now, there are two ways to do this. One way is just to create a new variable in your data set where it's, in our case, age times age. And that would be age squared. And then you could, maybe you call it age 2 and you say copper by female diabetes with age 2. You could do that, but you don't have to. You can create this interaction term here, either with a star or a by here. Okay, and that's easy enough to do. However, you can only do this with a covariate or a continuous variable. It has to be a variable that follows the keyword with. It cannot be a predictor that follows the SPSS keyword by. Okay, and then we have this here. Let's see here, there's all of our descriptive stuff, and here is our squared term here, this bottom one here. Okay, and then here are your parameter estimates here. Okay. We've got a domain subcommand that we can use. Now, these domain subcommands work differently than the subpop subcommands did for our continuous predictors. Okay, here you can only specify one variable, and in parentheses, you must specify the level of the variable for which you want the output. You can't specify, you know, regions 1 and 2 in the same call. If you want to see the output for regions 1 and 2 together, then you have to create a new variable that has regions 1 and 2 together, or you run the analysis once for region 1 and once for region 2. But this is the only way that you can specify the domain subcommand. You have a single variable and then the level of that variable for which you want your output. So here we have our outcome by female with height. And then here we have our output, and we have our output here, and this, all the tables have this population for the subcommand here. Okay. There's a custom subcommand, and I'm going to go through this part really quickly. And the reason is this is really complicated. And if this is the only part of the workshop that you say, gee, I didn't quite get all that, you're doing great. This custom subcommand is a combination of an L matrix and a K matrix subcommand that you may or may not have used in other parts of SPSS. This stuff is definitely not available through the point and click interface here. So let me give you some examples here. Well, let me go back here for a second here. The L matrix subcommand is used with contrast coefficients, and those contrast coefficients must sum to 0. The K matrix is used to test results of your output. Okay. If this sounds alien and foreign to you, we'll be done with this section very quickly. I wouldn't get too upset about it. Okay. So the first row of our L matrix tests the differences between levels 1 and 3 for race, and the second row tests the difference between levels 2 and 3 for race. We have our outcome variable, systolic blood pressure, predicted by race, and SMA, which is just another categorical variable here. And we included the interaction here. I usually use the labels. You'll see it in your output. It's just an attempt to keep everything kind of readable, understandable, especially as these get to be more and more complicated. So let's start. We have the custom subcommand here. Now notice that although these are on new lines, there is no /. They are not their own subcommands. This is all part of the one custom subcommand here, right? So do not go getting extra slashes in here because that will cause a problem. This here is race. This is 1 versus 3, which is that first one that we're doing. So 1 has a positive, versus means it's the negative, and 1 minus 1 equals 0. So they sum to 0. Here on the interaction, this is positive 1/3 distributed across the levels of SMSA. The second level is not involved here. And then here's the third level again, distributed as negative 1/3 so that it all sums out to 0. This semicolon is necessary here because now we're moving on to the second one, which is the difference between levels 2 and 3. So here, level 1 is given a contrast coefficient of 0. Level 2 is given a contrast coefficient of 1, and then the third level is given a contrast coefficient of -1. Since this is the first one, these are all zeros. These are positive 1/3 and negative 1/3. Yeah, it's a lot. Here is your output. It all looks very familiar. Here is your variable information. There's only the continuous outcome, so that's what you have the mean for. Here's your factor thing here. Despite the fact that it's coded 1, 2, 4, there's only 3 levels here. And then your R squared. Here's your test of model effects, which is really what we're here for, in your parameter estimates. What you're looking for here is this. This is your L1 and your L2. So this is race 1 compared to race 3, and this is race 2 compared to race 3. And so that's what you're looking for. And then here are your positive and negative 1/3. And this is what you really came here to get. Here is this test here. Okay, so that's the way that this works. I've got one more example. I'm sorry, it's even more complicated, but the reason I wanted to put this example in here is because people do ask about simple effects, and this is how you get the simple effects. So say race 1 versus race 2 is different between SMSA 1 and 2. So we'll just look through the syntax quickly here. Here's your custom subcommand. So we said race 1 and race 2. So this is 1, -1, and 0. And then here is your 1, 0, 0, -1, 0, 0. And since race 3 is not involved, these are zeros. And then here is the 1, -1, 0. And then these for these here. And now your K matrix here is the 1, -1 here. Yeah, it's a crazy lot. And if you think that's a lot, wait till you see the output. So here's our variable information, factor information. Here's our overall test of model effects. Here are your parameter estimates. And this is the output of the custom subcommand here. Here is L1 and L2. You want to look at this just to make sure that you and SPSS had clear communication. This is the test of L1, this is the test of L2, and this is the test that you're looking for here. Yep, it's an awful lot. I agree. But that's how you test simple effects. I'm sorry, I wish that there was an easier way of doing it. So let's step away from, yes.
So I matrix, K matrix, are you talking about the effect coding or contrast coding instead of doing just the dummy coding? What is the utility of I matrix and K matrix? Is this
Those are It is definitely not the way that you're coding your dummy variables. This is using contrast coefficients, which is different from the way that you code your dummy variables to test specific hypotheses.
So it's like a way of doing the contrast coding, or
They're
sometimes they call it
contrast
effect code.
coefficients used to test custom hypotheses.
Okay, so it's like a customizing, okay, different coefficient. Okay, I see. Okay,
Yes.
thank you.
So here are some more exercises here. You can try running a t-test. There's some other things here. And then our break, I'm sorry, the break is going to be really short. It's only going to be, we'll come back, I'll tell you what, we'll come back 2 minutes after the hour. Go ahead and try these exercises if you want. Get up and stretch or take a nap like the kitten here. And we are going to zoom through CS Logistic and CS Ordinal for the last hour of the workshop. But let's take a break now and come back at 2 minutes after the hour. If you have specific questions for me, I will stay here and answer questions. Okay, I'm going to stand up and stretch but I'm still actually here. If you have any questions, just unmute yourself and ask me, but I'm just going to stand up and stretch for a second. All right, it's 2 minutes past the hour. Thank you for hanging in there with me. Let's move on and cover the last two procedures that we're going to discuss today. We're going to start off with CS logistic. You use this when you have a binary outcome variable. So your outcome variable is coded 0, 1, or possibly missing. And the modeling of the predictors is exactly the same thing as in linear regression. So at least that part is easy. We're going to start by looking at the distribution of the binary outcome variable. I'm going to use high blood pressure, which is coded 0, 1, 0 if you do not have high blood pressure, 1 if you do. And I just want to have a quick peek at the distribution of the variable. And this is distributed approximately 63-37, which is not bad. But I do want to know that, because if you have a variable that's distributed something like 95-5, you could encounter estimation problems. Excuse me. And so you do want to have a good idea of how your outcome variable is distributed before you start doing logistic regression. And I would do this if it was a weighted or unweighted analysis. I always want to know how my binary outcome variable is distributed. If I'm going to use categorical predictors, then I might want to see how that distribution looks. So I'm going to use health as a categorical predictor in my upcoming models. So on my table subcommand here, I have health by high blood pressure. And then I have a table that looks like this. And really what I'm looking at here is my unweighted counts here. This 310, 419, 766, 904. I'm just looking for anything where the raw end might be going down kind of low, and I don't see anything like that. So I think that I am good to go. So we're going to use CS logistic, high blood pressure. Now, consistent with the rest of SPSS, by default, the highest numbered category is used as the reference. But typically in logistic, you want the 0 to be the reference, not the 1. And so you can have this keyword low in parentheses here to say that the lowest value, or the 0, should be the reference group. By means of categorical predictors coming. So health is going to be treated as categorical with the continuous predictor age. Here's our plan, which is the same thing that's been all along. Here we're just going to have the two main effects, health and age. I'm going to ask for some options here. I want the parameter. EXP is the exponentiated parameter, which is the odds ratio, the confidence interval, and the test statistic. And I want the tests adjusted for the sampling plan. All righty. So we've only got 2 missing cases. Woohoo! That's good news. Always want that. So here's the distribution of our outcome and our predictor here, our covariate thing. I skip over the pseudo R-squareds. The emphasis here is on pseudo, so I don't really care, you know, what they are. The only thing that these things are good for is if you're going to compare models, but that's really about all they're good for. So I don't pay much attention there. Here's your test of model effects. Health has multi-degrees of freedom because it's got 5 levels, so approximately 4 degrees of freedom here. And here is our adjusted F test, and then here is age. So here in this note here, the reference category is 0. That's what you want to see, because that's the interpretation most people are used to in a logistic regression here. But you can't change the reference group of the predictor, and that's why health equals 5 is the reference group, because again, SPSS uses the highest numbered category as the reference group here. So overall, the Variable health is a statistically significant predictor of the outcome, given that age is in the model here. And here are our odds ratios right here. So if you leave out the model subcommand, the result is exactly the same. So the default for model is to include the main effects and nothing else. So you don't actually have to put in the model subcommand. Personally, I always do. And that's because if I'm posting code online or I'm working with collaborators and we are sharing syntax, I don't want to have to expect them to know what the defaults are for each and every procedure. I put this in here so that there is no question what the model is. It tells you what the model is. But if you've had enough typing for the day and you want to leave that out, you can, and the output will be exactly the same. You can create an interaction term if you want. Here, I can create an interaction categorical by continuous interaction term. If I want to do that, I use the asterisks here. You'll see in a minute that you can use the keyword by. I've asked for all the stuff in my output. And here's your test of model effects. You see our interaction term here is statistically significant. And then here is our resulting output with the parameter estimates. These are your log odds, and these are your odds ratios. And very nicely, excuse me, you get the confidence intervals for both of those metrics. Keyword by right here. And the output is exactly the same. All right, here we're showing the use of the odds ratio subcommand here. Sorry, too much talking in too short a period of time.
Christine, do you want to take a minute? Yeah. Let's just give Christine a minute to recover, please. Thank you.
Okay, thank you. Sorry about that. The odds ratio subcommand is used when you want to compute model-based odds ratios for factors and or covariates. And you can use multiple odds ratio subcommands, and you can specify where the factors are going to be held, and you can specify where the covariates are going to be held. Now, one nice thing is that you can put in multiple values for your covariates. So I'm going to get output for age equals 30, age equals 50, and age equals 70 here. So this is our standard output that we expect to see. Here are your overall test of model effects here. And then here are our parameter estimates, our log odds and our odds ratios and all their confidence intervals. And then here we have multiple output tables, one for each of the odds ratio subcommands here. And these are calculating those specific odds ratios that we had requested. And the reason you might want to do this is to get the confidence intervals. This kind of thing you can probably get by doing some math yourself, but calculating the confidence interval would be a lot more work. And that's where the subcommand is useful for you here. And then the notes here remind you of what is done to get these values here. So where things are being held and such. Right, and so you have this, and then here we've got the 3 rows for our 30, 50, and 70 here, and then we can see our odds ratios. This kind of stuff I find is very helpful when you're writing something up or trying to make a point that, you know, as you get older, the odds ratio really goes up or whatever it is. It's typically not something where it's part of the original analysis, but this is you making the point of your paper, the point of your argument, and so it's helpful there. Of course, there's a domain subcommand here. Just to be different, I said rural equals 0, which means urban, right? And then again, you'll see the note at the bottom of all of the tables reminding you of the subpopulation specification here. And then you have your test and model effects, your parameter estimates as well. All right, so that was logistic regression. Does anybody have any questions regarding binary logistic regression? Okay, one other thing you can do with the CS logistic command is do multinomial logistic regression. Now, when do we use multinomial logistic regression? Anybody want to hazard a guess? When do you use multinomial logistic?
More than 2 categories?
Yes. Now, are the categories ordered or unordered?
I'm not sure.
Okay, that's fair enough. Typically used when they are unordered. If the categories are ordered like they are in my example with health, that ordering is ignored. All right, so multinomial logistic is used when you've got a nominal outcome variable that typically has more than 2 levels here. And it's a type of logistic regression here. What's interesting about this is that now this outcome variable has a reference group, and I've specified that it's going to be the lowest. I could have said high here and specified the highest number here. So let's see what our output looks like. This part here, the sampling design, categorical variable, covariate, all this looks very familiar. There's nothing new here. Here's our test of overall model effects. Where you start to see things that look different, this part of the output is level 2 compared to level 1 of the variable health. All right, health, because I said low in that keyword here, where I said low right here, that means the lowest numbered category is going to be used as my reference. And so this is 2 compared to 1. This is 3 compared to 1, 4 compared to 1, 5 compared to 1. And notice now I have coefficients and odds ratios for each of these different regression models. And I can test, you know, whether this, let's say, age is the same across these different equations or various things like that, if that's what I want to do. But the point is that it is treating this variable as if it does not have ordering. Okay, I didn't have another variable in the data set to really treat like that, but you can look at that and say, well, that's ordered. And you're right, it is ordered. So let's look over here at ordinal logistic regression. Here, your outcome has more than 2 levels, and they have some sort of natural ordering. It's often used when a scale is too compressed to be considered continuous, but you don't want too many levels in the outcome. Examples are something like small, medium, large, none, some, lots, 0, 1, 2 kind of thing. Another way to think about it is that they're ordered, but the distance between the points in your scale may not be equivalent. So the distance between none and some may be different than the difference between some and lots, right? And so, yes, it's ordered, but it's not continuous in the, you know, the difference between the different points on your scale are equivalent. Let's see here. It's actually under the hood a series of logistic regressions, and the levels of the outcome are collapsed going from lowest to highest or vice versa. It doesn't really matter. But what's happening here is that the coefficients in those logistic regressions are constrained to be equal. That means it's important to test whether these constraints are reasonable, and you do have an option for handling the situation in which that test of parallel lines is violated here. So let's see some examples here. I'm actually starting off here with a logistic regression using the CS ordinal command, just to show you that you can do it this way. The difference is that in an ordinal logistic, you're going to get a threshold rather than an intercept. So I have my model here by health with age. Here's health, age, and their interaction. And we get our output. We're very familiar with all of this. This looks, you know, like it does for all the other regression models here. Here is this. This is the output, and see that I have a threshold. I do not have an intercept. I have a threshold here. This is this minus 2.857. Here are my coefficients. Here, they are constrained to be the same across my 2 logistics. Excuse me. There's only one logistic here, so there's no constraint. Sorry, we're only in binary outcome, so only one model. Here's your output from CS logistic. Here's the intercept here, but these have different signs, the same value, but different signs. Right, and that's the parameterization using threshold and intercept here, but it's the same darn thing. The default here, the minimum you can get away with is CS ordinal, your outcome. I use descending, you can use ascending, whichever way you want it to go, up or down. And then I said by female region with age, and then we have our plan file. So based on what I said previously, what does our model look like? What is contained in our model? Does anybody know what predictors go into our model? Oh, come on, be brave. What are the predictors in our model? Female, region, and age, right? No interaction terms, just the main effects here of our predictors. So here we go. So let's see here, we had female, region, and age. Here is female, region, and age. So there we go. I personally don't find this to be terribly interesting though, because although I have my test of model effects, I don't have any coefficients. And if I'm going to report this I kind of have to have my coefficient, so I have to go use some subcommands. And this is where I'm going to use my statistics and my test subcommands. I want my parameter, I can exponentiate them. That gives me an odds ratio. I want my confidence intervals. I want my test statistics, and I want the tests adjusted for the sampling plan here. So here we go. This is the same that we had before. And then here is our output with our predictors. We can use a domain subcommand here, and this domain subcommand looks exactly like it did for CSGLM and CS logistic, in that I can only specify one variable and I can only have one category. So let me ask what may be an obvious question, but if I wanted rural by female, what would I do? If I wanted females living in a rural area, what would I do? Anybody? What would I do? I would simply create a new variable that had 4 levels: rural male, rural female, urban female, and then whatever code I had given to rural female, I would use right here. So this would be the name of my new variable, and then the level I had given it in the new variable. And that's how you would do it. You just have to create a new variable in SPSS to do that.
Hello, sorry. Oh, so may I know if I can use the syntax like a temporary select if, like just to temporarily select like a rural and okay.
Not in complex samples.
Okay, gotcha.
Yep. Good question though. Thank you. Yes.
So what's that used for? Like the sample with like small, like data with smaller sample size, or?
I'm sorry, what?
Yeah, sure. So if I want to use the select if like a syntax, like what kind of data set should I use?
Select if would be used with an unweighted data set.
Okay, gotcha. Thank you.
Yes. Another question?
Yeah, so in the domain subcommand, we can't use anything like, for example, female by rural or anything like that.
Not on the domain subcommand. You can on a subpop subcommand, but not on domain. And I don't know why the two operate so differently. That seems like a strange distinction to me. But here on the domain, you only get one level of one categorical variable. And so if you want, rural by female by age category or something like that, what you have to do is create a new variable in your data set, specify the name of that new variable here and the level that you want of that variable here. Does that make sense?
Sure, thank you.
Yes. Any other good questions? Because these have all been good questions, so I bet you have a good question too. Anybody else want to be brave? Okay. The output here you're already pretty familiar with, and then here is what we get. So we have the different thresholds because we have a threshold for each of the different regressions that was done here. And so we have these thresholds and then these parameters. These were constrained to be the same across all the different analyses that were done. So let's see what happens if, well, let's test and then see what happens if we violate the test. So we're going to use this non-parallel subcommand here. Test asks for the test to see if it is okay, if it makes sense for us to constrain these parameters to be the same. And then the parameter keyword is used to give us the output from a generalized ordinal logistic that would be used if we grossly violate the parallel lines assumption or grossly violate the assumption that it's okay to constrain these parameters to be the same across the different logistics. So it is true that it is easier to violate this test as your n goes up because you have more power to detect smaller and smaller effects that may in fact be trivial. And it is also true that you're more likely to violate this when there are more levels to your outcome variable because you're constraining more things to be the same. So let's go ahead and have a look at our output. All of this looks very familiar. Here's our test of model effects. And here is our output. So this part is all the same here. What's different here is these next two slides. This is your test of parallel lines. And what you were hoping for was that it would be not statistically significant. This says that we have somewhere along the way violated the assumption that all the coefficients could be constrained across the different logistic regressions. And then this here is the output that you get when you have the parameter keyword, and this is the output from a generalized ordinal logistic regression. And what you can see here is that the coefficient, let's just take the coefficient for the variable female here. See how it bounces around a little bit? And I bet this is the one, if this was the one that violated, I bet this would violate here, because this is essentially 1.6, this is 1.7, this is, oh, I guess this is negative here, so maybe this is what violated. But anyhow, you can see some of them are very, very similar, and then every once in a while you get somebody who's really very different. You can, of course, do this with a domain subcommand. I just wanted to put in a quick example of that. You're familiar with this kind of output, but I promised to put in all the output for you so you could see what it would look like. This is the output from the ordinal logistic. Here is the test telling us that it has been violated. And then here is the output for this model from the generalized ordinal logistic. So there's that here. Let's have a quick look at probit regression. I personally don't see a lot of probit. It is another model that can be used when your outcome is binary. It assumes that the probability of a positive outcome is determined by the standard normal cumulative distribution function. That's a whole lot of words. It just means that it's, you know, a positive, it's binary, and it comes from this kind of distribution here. The problem with probit is that although it has really good statistical properties, and that's why statisticians use it a lot, the coefficients do not have an easy or natural interpretation. So while the statisticians like it, the people who analyze and interpret the results of data analysts, they don't like this at all, because what am I supposed to do with this thing if it doesn't have a natural interpretation? So usually you just look at the sign of the coefficient and the statistical significance. For a lot of us, that's not so great. I want more than that. Does have different statistical properties than logit, and it's actually more commonly used in economics, but you don't see it so much in the social or the medical sciences. But I do bring it up that it is possible to get it using CS ordinal. It's not It's not in CS Logistic. CS Logistic really is using the logit link, and there's no changing the fact that it's using a logit link in that command. Here, you do have a link function. It's got a couple other options, but they're even less commonly used than probit. So I have our analysis here, and I've added this link function equals probit here. This part of your output looks exactly the same, exactly what you would want, but you have a threshold because we're in CS ordinal, so you have a threshold instead of a intercept, and then we have this coefficient, which I would not really interpret. I just say that it's negative, so it's got an inverse relationship with the outcome variable, and it is statistically significant. All righty, so we're kind of coming to the end of things. Let me ask, are there any questions on anything that I have covered up to this point? That's a lot of material. Any questions on anything that I have covered up to this point?
I have a question about creating a Flan file. Do we really need the three of them? Sampling weight, stratification variable, cluster variable. What if we don't have three of them? We just just two or one. Can still use the complex
Yes.
analysis?
Yes. You have to have, let me get down to that part here. So you want to create a plan file, you give it a name. You have to have a sampling weight. This won't work unless you have a sampling weight. However, I've never seen a publicly released complex survey data set that didn't have either a cluster or a PSU, excuse me, a cluster or a strata variable. So typically you have one or the other. Most often you have both of them, but you have to have one of them, I'm pretty sure. But the procedure will not run without this. So this is mandatory. Does that make sense?
So we can
Because
have
without
either,
this, then it's assuming that you have a simple random sample and the weight would be a constant across all elements of the population.
so at least we have two of them, right? Either sample weight plus the clusters or strata, right?
You must have the sample weight. You almost always have one or both of these, but
One
the
of-
procedure doesn't run without this.
Okay. And also I have a question about the confidence interval, 95 or 99 confidence interval.
Yes.
So we are actually having the entire, we are trying to have the entire population, right? So why
Yes,
do we
you're
still
trying to
need the
generalize to the population from this sample.
yeah, but this is a so we still estimating the population parameter.
You are attempting to estimate the population parameter from a sample.
So
Which is
this
why
is
you have a
still
confidence interval. If you had data from every element in the population, then you wouldn't have a confidence interval, you wouldn't have a standard error, you would just have the point estimate and you would know what the answer is. So for example, if you were going to look at the mean of age, where did I have this? If I had all of the ages of every individual in my population, this is the only thing I'd have in my output, and I wouldn't have these numbers here because I would know exactly what it is. But I'm estimating a value from a sample. And so I have these values here. If I collected another sample, I would hope that my estimate would be very similar to this, But depending on the size of the sample, this number could move around and hence these numbers could move around. So for example, if my sample was only half this size, I would expect my standard error to go up because I have less information on which to base my estimate. If this number doubled, I'd kind of expect this to go down because now I have more information in my data set to estimate this value. But even if I held it at this size, sample to sample, there will be some variability, and that's what's captured here.
Okay, I see. So still, this does not represent the entire population, right? So it
You
could
can
be one of the
generalize
samples.
from this sample to the population, but it's not, but it's still a sample. It's not that we collected information from every element in the population.
Okay, I see. Okay, thank you so much.
Yes. Another question?
Yes, so actually I have two questions. So first
Yes.
question, so what would you do if you would like to do like other analysis on complex data, like let's say factor analysis or clustering or any kind of analysis like that?
Sorry, but you'd have to move software packages. SPSS Complex Samples, I've run through almost everything that it does. So if you wanted to do factor analysis, you can use M+. Thought you could use Stata, could be mistaken on this. I'd probably pop over into M+ for a weighted EFA if you wanted to do that. I don't know anything that will do a weighted cluster analysis, at least not a traditional cluster analysis. But if you were going to do a latent class analysis, a weighted latent class analysis, that I know that you can do in M+, and I know you can do that in Stata as well.
Okay, thank you.
Yes. Any other questions at this time, please? Anybody else want to ask about any of the content that we've covered up to here?
So I know it's late and it's out of the scope probably, but would it be possible if you give like a very short tour of the menus, like how the graphical interface for complex surveys looks like in
Yes,
SPSS?
yes. So we're going to come to analyze. We're going to come to complex samples. And then just for a moment, let's come here to descriptives. Okay. I'm here. I select my plan file. Now you gotta wait for a minute while I go. There's a lot of stuff on my computer. It's in here, it's in here, it's here, it's here. We'll say continue. And now let's see here. I'm going to get the mean. Let's see here. I'm going to get for height and weight and I don't know, hemocrit and iron. So we can put that there. If I had a subpopulation, I could put it here. I can click on statistics. I can ask for a mean and or a sum. I can ask for t-tests for these if I wish to. I can ask for a confidence interval. Here's my unweighted count, my population size, my design effect. I've got a lot of stuff in my output. Let's click on continue. I can click on missing values here. This is variable by variable or listwise deletion. I'm going to use it like that. And then I'm going to say okie dokie. And so when I look here in my output, we see that SPSS has echoed the syntax and then put everything in my output that I have requested. Now, just to be clear here, SPSS capitalizes its keywords and stuff that it provides and then uses lowercase for stuff that you provide. But SPSS is not case sensitive. If you look at the code that I wrote, and this is on the website, all the code that I have in my file, I do not type in capitals. Okay, I simply don't. So you can see I have a star for starting a comment. It ends in a period. If I delete this period, everything is a comment until its next period. So I got to be careful there. And that it's all color coded to help you with things. But other than that, and I just go through and I type it out, or I copy and paste it and change some variable names. But that's what my syntax looks like. So if I double click into this, I can actually come in here and copy and paste this into my syntax file if this is an analysis that is meaningful to me and I want to capture. I can come back here to analyze complex samples. I can come here. Here's my general linear model. This is my GLM. It remembers this. I'll just say continue. And then I can put in my outcome variable, my factors, which are categorical predictor variables, covariates, which are continuous predictor variables. And then I have various things that I can click on. I can have main effects or custom. Here I would move over all of these. And if I wanted the interaction, then I could do this, put that in if I wanted. I definitely want to include an intercept in here and display statistics. Hypotheses tests. Here I usually want my adjusted F here. If I wanted to adjust for multiple comparisons, there are some options here. Estimated means, this is my EM means subcommand here. I can click this over here and say continue here. If I wanted to save stuff to my data file, I can, but these are the only things that I can save are predicted values and residuals. It's not all that helpful to me. And then here are some option. User missing, I still treat as invalid, and there's nothing else here. Oh, confidence interval. If you wanted to change this to a 90 or a 99%, you could do that there. And then I can say, okay. And again, here's the syntax that underlies the pointing and clicking that I did. And then here are all of my tables here. But as you saw, when I went to GLM here, things like the custom subcommand and some other things are not available here. They're only available through syntax. All right. One other thing I promised to do is walk you through the syntax guide here. So you see, here's your command name. The / indicates a subcommand. And then the stuff in the square brackets are optional. So you can see that in CS descriptives, the only thing that isn't optional is the plan file. Now, you have to have one of these three things, but you don't have to have all of them, and that's why they're all in square brackets. So usually they do give a little example here. It's not something you can run because it's not like there's a data set, but there's examples here. I typically read the basic specification because it will tell you what you have to do. So for some of them, they will say that you cannot shorten The subcommand names like statistics, you cannot shorten. It will tell you like your default. So anything that's in bold like this is a default. It will tell you if you need the round brackets or equal signs here. And it also tells you, for example, that the command will ignore weight in split file. So here are your syntax rules. You have to have a plan. You can have multiple instances of ratio, and they're treated independently. All the other subcommands can only be specified once. You can specify them in any order. You have to spell everything out. If there's an equal sign in the chart above, then you have to have it in your syntax here. Mean and sum can be specified without anything else, but that's not true of anything else. So when you see equal signs here, that equal sign is required. When you have an equal sign here, that is required. This is required. So I tend to read this, and then I can go look at anything else that may be of interest to me. And it goes through everything that is available to you. So here, you know, if you're going to put in a special value, it's square bracket, round parenthesis value, close all that. Here's your explanation of your subpop. This is where I got the maximum is 17. They can be string or numeric. Here's the difference between layered and separate. And it goes through all of your different, all the different commands, and they're listed in alphabetical order. So, you know, just scroll down until you find what you want. If you want stuff on the custom subcommand, click there. Here are all of your explanations and all of that. And every once in a while, you're lucky enough to get an example. I find the examples helpful, especially for complicated things like this. But
where
this is
can
the
I?
syntax. Yes?
Yeah, where can I download this syntax reference PDF?
Oh, you
please?
don't download it. It installed with SPSS. Look under help and command syntax reference.
Oh, I see. Okay.
Yes.
So,
And
so
so
this you are using 29, right? SPSS 20. Does the lower version also have this PDF reference as well?
every version of SPSS has this.
I see. Okay.
Yes, I
Okay, thank you.
guarantee you. I've been using SPSS since version 10, and I actually save, I'm so weird. I save the syntax files from all the different versions. So I have them saved on my computer. And so I can compare across them, because as a consultant, sometimes I get asked, well, you know, I'm using this version and I see this or I don't see this. And that way I can compare syntax files. But in every version of SPSS, you will have it, and it is located in exactly the same place. And it's called the same thing. That has been consistent across all the years of SPSS. All right, what other questions may I address for folks before we wrap it up? Okay, I've got one more. Try it yourself. I have some slides of references here. If you are new to the analysis of complex survey data, the book by Steve Frady and Pat is definitely the book you want to read. Get the second edition of it. They do not cover SPSS complex samples in the book, but it is the most readable, approachable book on the topic that you're gonna find here. There are some other classic references here, and let's see here. We have information on NHANES. There's a listserv that you can join. There are online tutorials for using NHANES data. These are very, very helpful. And after 186 slides, I would like to say thank you. Thank you for making it to the bitter end. If you have any last minute questions, I'll be around for a couple more minutes, and enjoy analyzing your complex survey data. Thank you.